Hi everyone. First of all, I'd like to thank the organizers because they gave me the opportunity to participate this year as a speaker. As 4 years ago, I participated by presenting a poster. And today, I'm going to talk about quantum gravitational decoherence from minimal length scale. And this presentation is essentially based upon a recent article that I've done in collaboration with Fabrizio Illuminati. And this is the reference in case you're interested. This is a brief outline of my presentation. I'm going to start by giving you a brief excursus on the generalized uncertainty principle and consequences that it entails at the level of standard quantum mechanics. And after that, by introducing a reasonable answers, I'm going to show you how, starting from this deformed quantum mechanics somehow, is it possible to reach a linear type master equation which should describe a universal decoherence mechanism. After this, I'm going to also discuss some experimental possibilities, in the sense that I'm going to show you an experiment which is capable of detecting this kind of decoherence mechanism, but actually not only this kind of gravitational decoherence mechanism, but different classes of gravitational decoherence mechanisms. And if I still have time, I'm also going to go through conclusions and future perspectives. Very good. Without further ado, let me start by telling you a couple of stuff on this so-called generalized uncertainty principle. So, as some of you know, there are many theories of quantum gravity that predict the existence of a minimal length scale, and such minimal length scale should modify, of course, the standard Heisenberg uncertainty principle, according to which, if you have a sufficiently high energy probe, you can resolve arbitrary small spatial distances, as conveyed by this inequality here. But in the presence of a minimal length scale, clearly this is no longer the case. And in particular, it was pointed out for the first time in the context of string theory that the first order perturbation to the uncertainty principle is given by this term over here, where the LP denotes the Planck length, because this effect is expected to become dominant at such length, at such scale. Originally, though, this beta parameter that I put here, which is called the deformation parameter, was missing, was absent, because it was basically implicitly set to 1. And there was only the plus sign, even though later on in literature it was argued that also scenarios with negative beta are compatible with physical phenomenology. And so for the moment, let me put this plus or minus sign here for convenience. A reassuring fact is that this kind of uncertainty principle is achieved not only in the context of quantum gravity models, but also in Gedanken experiments involving large and micro black holes, and as well as the gravitational Heisenberg microscope. And one last thing which will be relevant in a couple of slides is that starting from the generalized uncertainty principle, we can reverse the Robertson-Schrödinger prescription so as to recover a deformation of the canonical commutator between the position and momentum operator. And so if we started from the previous uncertainty relation, this is the deformed commutator that we obtain. Now, of course, this kind of generalization entails a lot of interesting consequences, level of standard quantum mechanics. There are a lot of results that have been obtained in research, so I'm going to simply list a couple of them just to give you the general idea. Of course, you get a minimal uncertainty position which is proportional to the Planck length, but you can also get spatial non-commutativity if you are in higher spatial dimensions, even though this kind of non-commutativity can be controlled so as to let it become manifest only at higher orders in this deformation parameter. And last but not least, you also have a sort of non-orthogonality of the formal position eigenstate, because the very definition of the position operator is kind of complex, but this lies beyond the purpose of this talk, so I'm not going to discuss about it. What I want to start from is this deformed commutator in higher spatial dimension, which is the most general one, which preserves isotropy and rotational invariance. And so, as you can see here, this is set in such a way that we can, at least in a first approximation, forget about spatial non-commutativity, as I've already anticipated. And a suitable representation for these operators is given by this choice that you can see in the second line. Basically, here in the second line, with the operators with the subscript not denote the operators that satisfy the standard Heisenberg algebra. And so you can see that we can use this kind of representation to see that now generic Hamiltonian can be now written as the sum of two distinct contributions, namely the unperturbed Hamiltonian, which is the kinetic plus potential term, even though the potential in this case will be neglected as we are considering simply non-interacting systems. And there's also a beta-dependent term that I've written up to the second order here, even though this kind of analysis will not affect the results that I'm going to show you. So basically this is the starting point, even though actually the starting point is the plus or minus sign that I've mentioned at the beginning. Because another fact that I haven't told you yet is that this deformation parameter is typically assumed to be of order 1 and is typically assumed to be a constant quantity. But as I've told you, there are scenarios in which are compatible with a positive value of beta, scenarios which are compatible with a negative value of beta. In a sense, our starting point was to try to solve this apparent conundrum by promoting this beta to a quantity which instead is no longer constant, and in particular, inspired somehow by the quantum fluctuation which are expected to become relevant as long as we approach the Planck length, we tried to equip this deformation parameter with a stochastic quantity, and in particular, the choice that you made is that this beta should be a constant such that by averaging over fluctuation you recover 1, which in a sense is in accordance with all the papers that say that the magnitude of beta is 1, and a stochastic function with sharp autocorrelation. And starting from these premises, we basically wanted to see what happens to the time evolution of a generic quantum system, or a relativistic quantum system in particular. And clearly we start from the Liouville von Neumann equation. We perform a couple of computations that I can skip for the moment. But in the end, basically we try to solve this by going into the interaction picture and reversing analysis, so showing a picture again, to see that now we are left with, by averaging over fluctuations, we are left with a limited time master equation, because apart from the usual unitary operator that you see here, there's also a non-unitary part, which is responsible of the coherence. This sigma, I forgot to mention that this short notation to indicate this fraction, where Tp, of course, is the Planck time. And this kind of limited time master equation entails interesting consequences, as I told you, because it is capable of giving an explanation for the loss of quantum coherence. In particular, it shows you how you start from a picture where Schrödinger's cat is both alive and dead to a picture in which Schrödinger's cat is instead either alive or dead. And if you recall the talk by Professor Wu, you have seen that in presence of this kind of limited time master equation, there is a localization in the energy space rather than in position space. And in fact, we can easily look at what happens in the position in the momentum space by looking at the differential equation which fulfilled by the maintenance of the density matrix. Instead, this is a linear differential equation. It can be easily solved by introducing this delta A. This way, you see that this is how the elements of the density matrix evolve in time. Regarding the diagonal part, you can easily see that this is not touched by the time evolution because the exponent here is the exponential of 0, so the 1 and the diagonal part is left untouched. But the off-diagonal term, which instead contains the information of quantum interference, apart from the usual unitary evolution, presents this kind of non-unitary evolution, which instead is a damping term, because it's a real exponential. Thank you. And this damping term basically allows for the degradation of these diagonal elements, thus washing out somehow the phenomenon of quantum interference. And in particular, the characteristic time for this phenomenon is the so-called decoherence time, which for the model that we have considered so far is equal to this quantity. Now, this is a contour plot of the logarithm of the decoherence time as a function of the energy and the mass of the system that we're considering. And so you can see that as long as we approach the mesoscopic scales, so when we increase the energy and the mass of the systems, basically the decoherence time tends to get smaller and smaller, which means that quantum interference is washed out extremely fast. And in fact, just to give you a rough idea of what happens, In this table we summarize a couple of examples of classical systems which have a value of the decoherence time which is extremely small, and intrinsically quantum system which instead exhibit a decoherence time which is far greater than the age of the universe. But of course, as you have seen also from the talks by Professor Wu, Professor Diosi, this is not the only gravitational decoherence mechanism that has been proposed in literature. And in fact, we also in our work compared different gravitational decoherence mechanisms. And in particular, we saw how the decoherence time behaves in terms of the Planck energy, the average energy of the system, and the h bar. And clearly all these decoherence mechanisms agree at the Planck scale, but our gravitational decoherence model predicts the longest decoherence time below the Planck scale, so when we approach the Planck regime, and the shortest decoherence time when we go towards the mesoscopic scales. So, theoretically speaking, we can say so far so good, but the point is there a way to detect this kind of phenomenon? And in particular, is there also a way to discriminate among all these predictions? Well, the answer is yes, and in fact this kind of the decoherence mechanism can be probed by resorting to capital mechanics. So very quickly, this is the sketch of the experimental setup, which in particular you prepare two single photon sources in a maximally entangled state, and you put these single photon sources in two distinct cavities, optomechanical cavities, one which is susceptible to gravitational decoherence and one which is not. And in both cases, of course, as the experiment is performed at finite temperature, you have decoherence due to mechanical heating of the system. And at this point, we can verify, we can measure the amount of decoherence, so the loss of quantum coherence, in terms of the degradation of the correlations shared by the initial maximal entangled state. In the sense that here decoherence can be viewed somehow as a transfer of quantum information from the two single photon sources to each of the photon sources with the environment. And so, basically, the best way to measure the quantum correlation shared by a system is to rely on a GHSH experiment, so a Bell-type experiment, but in the version due to Clauseron, Shimon, and Holt. And in particular, as you can see here, this is how the correlation between the initially maximally entangled state is degraded over time. And the blue curve denotes the degradation in presence of mechanical heating only, whereas the red curve takes also into account the presence of the gravitational decoherence mechanism, if there's any. And as you can see, for a suitable choice of the experimental parameters, in particular when we require temperatures to be extremely low, so the order of 10 nanokelvins, and masses of the order of 10 to minus 14 kilograms, which interestingly is the same order of magnitude required by QGEM experiments, you can see that the gap between these two predicted curves is of the order of 10 to minus 2 seconds, which means that this kind of gap is experimentally accessible. And this kind of experiment has been proposed in this reference, but the same experiment is also capable of discriminating between different gravitational decoherence mechanisms, as we have proposed in a follow-up of the work that I've mentioned at the beginning. This has been done with Issa, Soria, and Elias. Of course, there was also Fabrizio, hopefully. And in this work, we basically showed that if we start from a completely different generalized uncertainty principle, which is compatible with doubly special relativity, we can see that the predicted loss of quantum correlation occurs at timescales which are extremely small if compared to what we have shown before. So it's almost instantaneous in the temporal scales of the other phenomenon. And so basically this experiment is, would be extremely important and would tell us if there's actually a gravitational decoherence mechanism. And since I guess that there's only a couple of minutes left, I'm going to conclude by telling you that in essence what I showed you is a decoherence mechanism, a mechanism which is capable of explaining the quantum crustal transition, which relies on the existence of fluctuating minimum length. Of course, this is only the beginning of our work, because further developments of the model described so far can help us to find the optimal experimental window where to investigate, but it would also allow us, in principle, to propose other low energy and relativistic laboratory tests, just like the one that Alfredo mentioned on Monday in his talk. And just another side remark, one last consideration, is that I have described the coherence phenomenon which predicts energy localization. But in principle, this localization can be accompanied also by spatial localization if we require the existence of a minimal momentum scale as well. But we are still trying to look for the optimal way how to realize this. So it's still a work in progress. And I guess my time is done, and I'd like to thank you for your attention. Thank you very much.
Yes, please.
The chi that you wrote down, the stochastic part, with the average being 1/TP and the correlation being delta. What did you do after that? How did you get the master equation?
Well, basically, yeah, here I skipped this part because basically switched analysis into an interaction picture. You get something which can be truncated because, as I told you, this effect is extremely small. At this point, you are left with this expression in the interaction picture. And here you average over fluctuations with these requirements over here.
So this chi was put in the master equation and average?
Yeah, because in the master equation you see that this Hamiltonian, which is beta dependent, contains the information on beta, and beta has this function of chi. So you average over fluctuations and you reach this expression, you reverse the analysis in the Schrödinger picture.
Thank you.
Yes.
Thank you. My question was partly the same, actually. I'm somewhat skeptical that this really makes sense unless you're putting in an explicit fluctuating field in some sense. But granted the framework, how is it that this does not interfere with interference in generic quantum experiments? This would be a ubiquitous phenomenon if it were present. So how can you explain that?
Yeah, but since this is since this is an effect which would be relevant, as I said, that the Planck scale, I mean, this kind of decoherence mechanism is, as I told you, the experimental setting to detect this kind of decoherence is extremely precise. I mean, you should require to determine temperatures, extremely low, etc. Yeah.
Yeah, but you could conduct an experiment over many hours involving a quantum entanglement, a state of superposition. Over sufficient time, surely this would.
Well,
he showed the time. So
yeah, no, I showed the time, yeah, but I guess he was aware of the fact of the.
You mean the microscopic bodies? You're saying?
Oh yes, of course.
Yeah. Well, the car was what was it? I don't remember. The car, yeah.
Yeah, no, man, yeah, this is.
Which is a concern because it would interfere with what we would ordinarily see with sustained coherence over long periods of time.
For microscopic bodies.
Yes, please.
So I think the question.
I think we should.
Okay.
Yeah. Let's go to the. Sorry. Professor Time and then.
Okay. Thank you for a nice talk. As you know, in holographic theories of quantum gravity, the information in a region grows as the area of the boundary, not as the volume of the region. It is a consequence of that the minimum of length is not fixed at Planck length, but grows in proportion to the length being measured. Delta L is like L to the power 1 over n, where say n could be 3. This was, for example, the model developed by Carogliazzi for gravitationally induced decoherence. Somehow, this holographic length uncertainty seemed more reasonable than fixing it at Planck length. Would you consider trying decoherence in this holographic length uncertainty case?
Yeah, well, in principle, this can be done. I guess. I mean, it's pretty straightforward. I think. Well, at this point, you should look at how the decoherence times and all the standing phenomenology emerge. But I don't know if. But here, I don't know what can come out. I mean, at the level of numbers of numerical predictions. But yeah, this is something that could definitely be done.
Okay, sorry, we are really running. We can